as I said, this is some sort of ongoing work. I mean, part of it has been submitted, but not published yet. So it's about machine learning guided program synthesis and how we can sort of improve the performances, kind of keeping all the existing ideas in place. We'll talk about this, but improving on the algorithmic side. So maybe one inspiration, one kind of nice result that happened recently is this TF coder. So TF is TensorFlow. It's this very nice tool that takes input-output examples. So input outputs would be a pair of tensors, like so. This would be your input, and this is your output. And then TF coder comes up with this typical Python one-liners that would take you minutes, if not hours, to write down, and obviously is just what you were looking for. So TF coder is very successful at coming up with these things, combining one of these 500 functions that are defined in TensorFlow for manipulating tensors. All right. So more generally, the setup of program synthesis I'm looking at is programming by example. So that means that we have some input outputs, typically one or maybe a few, like up to, let's say, 5. And from these input output, we're interested in constructing a program that just maps this input to that output. And sometimes you ask the question, well, is this the right program? What if there are many solutions or anything like this? I will not consider that here. I'm interested in any program that maps this input to that output. So another point is that I'll be using a DSL, and although this is not what Vadim wants to do, but in many cases, actually, DSLs, domain-specific languages, are a good place to start because those are very simple programming language that are very specific to the task that you want to look at. And because they're very specific, they will be much easier to search through. And that makes the whole solution kind of more efficient towards solving a particular task. So here's just a simple example to get familiar with what it is. So I'm saying a program. Here I have some if then else construction, if some condition, then some program or some other program. A program can also just be some expression, then a condition may be inequality or equality, and an expression is using variables or maybe sums of variables. So a typical program I can have generated by this context-free grammar is if x is smaller than y, then y else x, which is basically just computing the max of x and y. Right? And then what do we do with these context-free grammars? One thing we can do is make them probabilistic. So now context-free grammars are kind of non-deterministic, right? A program is either an if-then-else or an expression. Now, if I add probabilities all over the place for every derivation, then I'm making this probabilistic, saying a program with priority half, it's an if-then-else, and priority half, it's an expression. So what it means is that now I have not anymore a set of programs, I have a distribution of programs. And this is the tool, this is what I'll be working with. So I'll call it a line of attack. It's kind of maybe one sort of set of techniques that's been used in so many recent program synthesis tools is the following 2 steps solution. The first step is learning a PCFG, a priority context-free grammar. So what do I mean by this? This is a pre-processing step, or if you want, the training step. So you just construct a neural network here, and what you expect your neural network to do is it takes as input one pair of input outputs, right? And what it outputs is probabilistic weight on the context-free grammar you started with, right? So in your program synthesis question, there is attached to it a context-free grammar that defines all the programs you are considering and that may be solution to your question. And now when you have an input output, then what you want to have is some sort of indications or predictions on what programs from this context-free grammar may be solutions. So the neural network will get you exactly that. It is fed with input-outputs, and what it gives you is probabilistic weights on the CFG, effectively turning the CFG into a PCFG. And now the idea is that, this is what's summarized here, the most likely programs for the PCFG are the most likely to be solutions. So if some program is given a high weight, a high probability in the PCFG, it means it's likely to be a solution. And so now you can imagine what will be the step 2. I'm skipping some details here. What is the step 2? Well, step 2 is the solution time. So now you're given a concrete input-output, and you want to find your program. So what you do is you have your trained model, you feed it with the input-output. Now you have a PCFG, meaning you have a distribution of programs. Now you can search through programs using that PCFG. So what does it mean using? That's the key. So there are kind of 2 natural approaches. If you have your PCFG, you can either start enumerating programs or you can start sampling programs, right? Maybe sampling is the most natural. You have a distribution of programs. Well, you just repeatedly sample from it until the program you sample is a solution to your question. Enumerating is maybe a bit is kind of the second guess you would have is you will just enumerate programs. Sorry, P3 and so on, with the idea that let me write D for the probability of the program according to my distribution. Then P1 is the most likely program, P2 is the second most likely, and so on and so forth. So I'm enumerating programs in decreasing order of likelihood according to my distribution.
Yeah. Isn't it non-trivial in itself, like ordering them in this order?
Exactly. Thank you very much. I think you have, spoiler. This is actually the point that I want to make, is that, somehow for a while we've been doing this, enumerating programs or trying to enumerate programs in the right order. So what I want to argue is that this actually is not such an easy task. And if you want to do it efficiently, then maybe you should compromise, first of all, meaning maybe you don't want to exactly enumerate in that precise order. You're happy if you can enumerate faster, but programs that may not be as likely. And the second thing is that I think this sampling idea, although very basic and very natural, has been kind of overlooked as a solution concept. So what I want to really advocate is that these 2 approaches are kind of complementary. Enumerating is good, but it may be expensive and hard. So here we want to compromise to get more efficient algorithms that will enumerate more programs, although potentially a bit less likely. And we should combine this with sampling algorithms kind of on the side. Imagine some parallel architecture where you would have one worker devoted to sampling, another one devoted to enumerating, and using both of these in order to find the right program. So this is some sort of generic slide about all the challenges that we have in implementing this line of attack, and this is why there are so many papers that essentially try to use different approaches for implementing this line of attack. So what I want to focus on today is this search algorithms. What's the best sampling algorithm and what's the best enumeration algorithm, and how should we think about this thing? Okay, I'll just keep this idea, although so I have some slides here that are about the pre-processing step. I think that's another very interesting question, but I want to skip it for now, unless we want to discuss that later. This is just some ideas that say that data generation is actually also something that should be discussed and looked at carefully. And better data generation ideas can lead to better performances overall. So let me go to the other thing, which is this search question. I'll make it completely abstract, maybe to see kind of more clearly what the question is. So imagine you have a known distribution on program, right? So in our particular scenario, it's given by a PCFG, but you can imagine that there's just some distribution on program. So every program has some probability. And now imagine the following game. It's some sort of mastermind game. The master samples a program according to the distribution D, and it's a secret program P. And now what you want to do is just, you want to find it. The only thing you can do is give a program and say, is this the right program? And if the answer is yes, then you're done. If the answer is no, then you just continue trying new programs, right? So you just make sequentially choices of programs until you find the right one. And now the natural question, what you want to do is you want to minimize in expectation the number of tries before finding P, where P sampled according to this known distribution D. Another point is that, if I didn't know D, then I would basically have nothing to say because I would have to try all programs. But the point is that because I know the distribution D, then I have some very important information. For instance, it looks very natural to start by programs that are the most likely. So this is some sort of abstract question that helps us think about this enumeration question. So now let me just tell you a quick riddle before I state the main result. It's the following. So imagine this is a very kind of the simplest scenario you can imagine. The master has a biased coin, and the probabilities are, well, actually, let me make it general, P1 minus P, right? So with priority P, you have head, and with priority 1 minus P, you get tail. So the master tosses the coin. I know you want to guess if it's head or tail, right? So obviously, a naive strategy would just be, if P is more than half, then you start with head. And if it's not head, then it's tail. So you're just making two guesses. This is an enumeration strategy, and that's kind of obvious. Now imagine that you want to do sampling. So what it means that you're doing sampling, it means that you don't have any memory. The only thing you're doing is at every point, you're sampling from your distribution, and you just output that. So what it means is your distribution is some P prime. So you're doing this with priority P prime, you have head, and priority 1 minus P prime, you have tail. Another question is, how should you choose P prime? So the obvious guess, and for some time we even overlooked that question, and for us it was obvious that P prime should be equal to P. Because if you want to match some distribution, then the best you should do is simply, imitate it. Turns out that when you do the math, what you're trying to do, you're finding P prime minimizing P prime over P plus 1 minus P prime over 1 minus P. And you do the math and you realize that the minimum is actually this weird number. That is essentially square root of P renormalized. And if you want to get a bit more intuition, imagine that this is 0, 1, this is a half. So let's say P is somewhere here. Then the optimal P prime will be somewhere here. So it's a bit kind of moved toward uniform, but of course biased by the original P. So this is the riddle. And now actually there's a much more general theorem that says exactly that. The optimal sampling algorithm is some D prime. So maybe I should say the optimal sampling algorithm against the distribution D is some distribution D prime defined as follows. D prime of P is essentially just square root of D. But this is not a distribution, so you need to renormalize it. So you take all programs and you just divide it like this. And now the good news is that if D was given by a PCFG, which is what typically we have in program synthesis, then this D prime can also be given by a PCFG. And this can be actually efficiently computed. So now what it means is that now we have a good understanding of what kind of sampling algorithm we should use. This square root sampling, we call it. And we can actually implement it practically. So I'm skipping a lot of things about enumeration. Enumeration is also very interesting. There's this illustration here. So this should be read from left to right. This is a sequence of programs. So each of these is a line of white and black of length 8. So those are programs, those are kind of programs of a bit of length 8. And this is the sequence of most likely to least likely program for some very simple PCFG. So the point is that, maybe I'll remove these colors. The point is that, as you can see, this order is kind of chaotic, right? Going from one column to the next one seems to be maybe not random, but complicated thing. So this kind of shows this trade-off. And maybe the cost of producing the exact most likely program after the one you just tried may be very high. So you kind of want to balance this with the likelihood of the program and have enumeration ideas that, maybe weave this around and do not exactly follow that order in order to be able to generate more programs. So just to give some, empirical data, what we did was implementing all the algorithms that we found in existing program synthesis tools. So there's threshold search, sort and add from the deep coder paper, A star, which is a typical algorithm in that setting, and our two new algorithms, square root sampling and an enumeration algorithm that we call heap search. And now we have both log scales here and there. So probability is the probabilities of the programs, right? So here this is a program that's rather likely, and here this is a program that's very unlikely to be generated by a grammar. And now this is how long it takes to find it, right? So 10 to the minus 3 is very quick, and 10 seconds already takes a bit of time. Now every dot in this graph is a single program and how long it took to find it. So on the right hand side, we have, here kind of likely programs took a short time to get found, and least likely programs, took much longer. So now clearly the best algorithm is this deterministic one, our new heap search, that outperforms in particular by one order of magnitude the A star algorithm. And the other thing you can see, I don't know if you see it very clearly, because those dots, in many cases, the sampling algorithm, so those brown dots, is in many cases faster than the deterministic heap search, but in some cases slower, right? So kind of the conclusion of this is that you should try to get the best of both worlds. On the other hand, have some deterministic enumeration, that's this guy here, and then also try your luck with sampling algorithms that sometimes very efficiently finds unlikely programs. All right, so I'm done here. This is a quick overview of what we've been doing recently. I'm happy to discuss that any further. I'll take questions.
Yes. So I actually ran into this problem recently, and that's why I guessed what the problem is. And what I thought of and what I implemented was just a neural network that produces the program to optimize the probability. Because this is really similar to the actor-critic framework in reinforcement learning, right? We have a critic that tells us a neural network that tells us how good any action is. But the action space is so complex that we can't sample from it. And so we make a second neural network that just outputs an action, and we train it to optimize for the critic. And it would be interesting to see a neural network in those comparison of methods.
So I guess, okay, so that's a very interesting idea that we haven't tried, and it would be very nice to compare it to what we have. Maybe one difficulty is that the programs have some structure, right? The programs are coming from the grammar. And so they're not, I guess the set of actions you have is like the real numbers or something like this.
Yeah, it's simpler, definitely.
So it's simpler. I mean, it's simpler and harder, but kind of it doesn't have structure. So the question is, how would the neural network kind of, get an idea of all of a sudden have some big program and then a short program, or how would it navigate these things? But anyway, that doesn't preclude this from trying. So yeah, that would be really nice. That's a very nice suggestion. Maybe we should discuss this further.
Yeah, it's not immediately obvious how would that neural network would look like. But this might be something like LSTM, which would also be probabilistic, right? But it will be given probabilities of characters, and those are easy to sample.
Right. All right. But what do you mean by characters? You mean every primitive of the program?
It can be tokens of the program. Yeah. So, or it can be something even simple. Well, I guess tokens of the program would be the easiest. So it would be something like an RNN that would predict the next token.
All right. That's an interesting idea. So the thing is, okay, I have a small concern when I'm thinking about it a bit more, is that what you would like to do is actually be able to, enumerate, sheetloads of program per second. And querying the RNN has a non-zero cost. I don't know how that factors in. I mean, I don't know if that would be a bottleneck, but it may be a bit costly for any program to use a network to ask for it. You see what I mean?
Yeah, definitely. It's a lot simpler than querying the original distribution, right? But
right.
Yeah, it still can be a bottleneck.
So, for instance, one thing that's funny is, when you do these predictions, there are kind of two natural approaches. Are you doing predictions once and for all when you do the search, or are you, when you have a partial program, are you querying again the network to get more predictions using your partial solution? And that creates a bottleneck as well. If you're doing too many queries on your prediction model, then you're just spending most of your time asking for predictions and not enough time on evaluation of actual programs. So this is another situation where you're becoming too greedy on predictions, and that kind of makes it ineffective. I mean, I'm not saying that this is the same, but I'm saying there are cases where querying the models too often is costly.
Yeah, the actor critic framework isn't the perfect fit, because here we are interested in enumerating the solutions, and in actor critic we would like ideally to take the optimal action every time. So the actor critic framework optimizes for finding one optimal solution.
Yeah, and then it will not give you an actual diversity, right? Because what you actually want is maybe the 1 or 2 million most likely programs. And the actor critic, as you said, will give you the first one, and then maybe you'll get the second one or something, but you want 1 million or 2. I mean, or whatever number, but yeah.
I still think there's somewhere where you can plug in a neural network, because the task sounds like we have something that's every time we have a task where the result is easy to measure, right, how probable it is, but it's hard to obtain. That can be trained. You just have to think about the right architecture. But yeah, don't have a solution at the moment.
Yeah. No, but that's interesting.
I guess I'll send you an email if I think of something.
Excellent.